Well, hello. I'm going to talk about the statistical methods in cosmology. And let's start with the definition of probability. We have two views. Frequentist view, which talks about the relative frequencies of events in infinitely long trials, while Bayesian view is expressing our degrees of belief or confidence in an event or hypothesis, which is particularly relevant in cosmology for interpreting experiments and observations since we only have one universe to observe. All right, so what is Bayes' theorem? Well, it helps us to update our belief in the model by incorporating the new evidence or the data. Here you see the posterior, which is the probability of a hypothesis given the observed data, and is estimated by the multiplication of the prior times the likelihood. The prior is the initial probability assigned to the hypothesis before considering the data, while the likelihood is the probability of observing the data given the hypothesis. Together combined, we are able to update our understanding of parameters and the models based on the observational data. So what do we need to use this theorem? Well, we need our hypothesis for sure, a model, and then the data, the priors, and the likelihoods. Next step is sampling. Well, we have a huge parameter space which we need to explore, right? The thing is, we need to use the sampler, which is a random number generator, and it seems easy, right? Because if we want to generate from simple distribution, it's fine, but as soon as we go to an arbitrary multivariate distribution like Bayesian posterior, it's going to be very hard to efficiently generate the random numbers. One could ask, well, why not just directly exploring the posterior? Well, the thing is, let's take the 6-parameter lambda CDM model. It requires 10 to 12 evaluations for only 100 grid points in each direction. Apart from being time consuming, it's very computationally expensive. So what is our solution here? We can generate samples from the distribution. And to do so, we have the Markov chain Monte Carlo method, and one of the algorithms that can be used is Metropolis Hastings. We're going to start with the proposal distribution, and we have a initial state. What is next? We need to generate random state according to that proposal distribution. And now we are calculating the acceptance ratio. Now we need to decide whether to accept the new point or to reject it. To do so, we generate a uniform random number, u, from the interval 0 to 1. If this new number is smaller than our acceptance ratio, we accept the new point with a certain probability. Otherwise, we're going to reject the point and set the next point to the previous point. And we're going to repeat this until we have our parameter space sampled. And now we're ready to do some calculations and statistics. For example, we can explore our models and parameters using the chi-square statistics, which is a difference between the observed data points and the expected data. Well, as you can see, it's a very useful tool in cosmology since it's talk about the goodness of fit of a model to the observed data. If it's too big, it means that the model is not doing well predicting the observed data. If it's too small, it may be because we are overfitting, meaning having so many parameters. Um, Another thing is, yes, uh, we can study the relations between parameters using the covariance matrix. In the diagonal axis, you see the marginalized variances and the off-diagonal components in which you can see the correlation coefficient rho. And this tells you about how correlated or uncorrelated the parameters are. If it's zero, it means that the uh, points are independent of each other. Another useful tool is the Fisher matrix for optimizing the experimental design and forecasting errors. We can use it to have an estimate of the uncertainties before conducting the experiment, and it's basically the inverse of the covariance matrix. And with this, I conclude my presentation. Thank you.